All right, welcome. We're going to do a series of videos this time for the lesson. We're going to try it like this so I can break it up into smaller videos and hopefully make it a little easier on y'all. But this we're going to do topic 8.7 in the CED for AP Calculus. We're going to do the volumes with cross sections, squares, and rectangles. To do this, our goal is to calculate the volumes of solids with known cross section using definite integrals. And we are going to follow this plan. We're going to first start by reviewing how to calculate the area under a curve and the area bounded by two curves. That's going to be an integral part of what we do today. So we're going to look at some simple curves here, and we're going to find the area under the curve. Let's start with f of x equals x. If we were to graph this, we know that this curve is just a line. It cuts the first and third quadrants in half. And if we were going to evaluate the area from 1 to x equals 3, area under the curve, then we would be looking at this area in here. It's important to know that what we're doing, let's go ahead and erase that real quick. When we do that, we're actually, get a different color. We are taking a sum. When you set up the definite integral, we are going to take the sum of the areas of an infinite number of rectangles where the width is dx and the height is the y value of this curve, which in this case is just x. If this is x, the width of that rectangle is dx, and the height is also x because the curve y equals x. So we're going to integrate from 1 to 3, the lower bound to the upper bound, the curve y equals x times dx. This represents the height of the rectangle. This represents the width of the rectangle. And the integral is the sum of an infinite number of those rectangles. And that's what we're doing. We calculate the integral. You know the integral is also the antiderivative. The antiderivative of x is 1/2 x squared. And we evaluate that from 1 to 3. So we end up with, we put in 3 first, well, 1/2 times 3 squared minus 1/2 times 1 squared, which is equal to 9, oops, it's 9, 1/2. 9 halves minus 1/2, which is just 8 halves or 4. If we're going to do g of x, then we're looking at the curve y equals x squared, which we know is a parabola. Let's say we're going to evaluate that one from -2 to 3. Then we know we're looking for the area, in here and in here. And we do that again with the definite integral. So we integrate from our lower bound to our upper bound. The curve is x squared times dx. Again, the height of each of these rectangles is x squared for a particular x, and the width is dx. And this all takes the sum, finds the sum of an infinite number of those rectangles as dx goes to 0. That's what the definite integral does. And so this becomes the antiderivative of x squared, which is 1/3 x cubed, evaluated from -2 to 3, which is 1/3 times 3 cubed minus 1/3 times -2 cubed, which is 27 over 3 is 9. And this is going to be -8 over 3. So it's going to be positive 8/3. And 9/3 is 27/3. So that's going to altogether be 35/3. That's how we do those. Let's go ahead and do h of x equals sine x. Let's evaluate this one from 0 to pi. Remember the sine curve looks like this, where it intersects the origin, and then this would be pi. So if we do 0 to pi, we're looking for the area under there. And we would evaluate that. Limits of integration from 0 to pi. y value of the rectangles, the height of the rectangle is sine x, multiplied times the width of the rectangles is dx. Antiderivative of sine x is negative cosine x, evaluated from 0 to pi. And so when we do this, we get negative cosine pi minus negative cosine 0. Cosine pi is -1, so negative 1 is +1, and negative cosine 0 is 1, so inside the parentheses is -1, so we minus -1, that makes +1. So the integral area from 0 to pi, the infinite sum of those rectangles, is 2. Let's look real quick at the area between two curves. And this time, let's look at the difference between the curve. Oops, draw. Y equals x and y equals x squared. So now we're looking for this area. And again, it's made up of an infinite number of rectangles with width dx. The height this time is the top curve minus the bottom curve. So if we're looking for the area, the region bounded by those two curves, we need to find where those two intersect to identify that region. So to find the intersection, we set the two curves equal to each other. We solve this equation. Remember, to solve a quadratic equation, we get everything equal to 0. And if we can, we factor. So we factor out the x. This means x times x minus 1 is 0. So x equals 0 is one solution, and x equals 1 is the other solution. Those are the points of intersection. So when we find the area between those two curves, we're going to do, the integral from the lower bound of the intersection to the upper bound of the intersection. And now we're going to do top curve minus bottom curve. The highest curve minus bottom. So this is going to be x minus x squared, and all that times dx, because that's going to give us the area of each of those individual rectangles that we're summing an infinite number of. The antiderivative of x is 1/2 x squared. The antiderivative of x squared is 1/3 x cubed. And we evaluate that from 0 to 1. So when we plug in 1, we get 1/2 1 squared minus 1/3 1 squared minus, now 1/2 times 0 squared minus 1/3 times 0 squared. Of course, this all goes to 0. That leaves me with 1/2 minus 1/3. Common denominator, that's 3/6 minus 2/6 equals 1/6. Of course, if you're doing this on an FRQ, you could have left it unsimplified here and gotten the answer correct. That is the reviewing the area between two curves and under a curve. And that's the first segment of this 8.7 lesson.